A ghostly light fills the entire sky, yet it remains completely invisible to our eyes. This is the cosmic X-ray background, a faint, permanent glow of high-energy radiation that has mystified scientists since its accidental discovery decades ago. It is the universe's greatest unsolved puzzle, a silent hum of X-rays coming from everywhere at once. By the end of this exploration, you will know the 25 most profound secrets this background light holds. We will investigate where this pervasive energy comes from, whether it reveals hidden black holes, and if it could even be a signal from the dark matter that shapes the cosmos. Each mystery pulls back a curtain on a universe far stranger and more violent than we ever suspected. What do you think is the most surprising thing hidden in the darkness? The very first mystery begins with a simple, haunting question. What is the source of this ghostly light? The discovery itself was an accident, a cosmic surprise captured by the earliest X-ray satellites sent to look at individual stars. Instead of finding isolated points of light, their instruments detected a faint, uniform glow coming from every direction, a permanent X-ray fog that filled the entire sky. It was as if the universe itself was humming a high-energy tune. The initial theories to explain this were as grand as the phenomenon itself. One idea proposed a vast, superheated gas, a million-degree plasma filling the unimaginable voids between galaxies. Another, equally compelling theory suggested the glow was not a true fog at all, but an illusion created by the combined light of billions upon billions of distant objects, each one too faint to be seen individually, like a sky filled with distant fireflies whose collective glow appears as a single, continuous radiance. The challenge in solving this first and most fundamental mystery lies in the nature of the light itself. Separating the glow of a true, diffuse gas from the combined starlight of countless hidden sources is a monumental task for high-energy astrophysics. It requires instruments of incredible sensitivity, capable of resolving the faintest of whispers from the deepest corners of space. Until we can peel back the layers of this cosmic onion, the true origin of the X-ray fog remains the primary enigma, the question upon which all other mysteries depend. This pervasive X-ray fog, however, was not truly uniform. As our telescopes grew sharper, they revealed a stunning truth hidden within the glow. Peering deep into the darkness, observatories like Chandra and XMM Newton resolved millions of distinct point-like sources. Each one is a tiny, brilliant pinprick of high-energy light. Yet for the vast majority of these sources, there is nothing to see. When astronomers turn their optical and infrared telescopes to the exact same coordinates, they find only empty space. These are the ghosts within the fog, a population of powerful objects that are completely invisible to our normal eyes. Identifying what they are has become a cosmic detective story of the highest order. The suspects on the list are all fascinating. They could be isolated neutron stars, the incredibly dense, spinning corpses of dead suns blazing with X-ray energy. They might be white dwarfs pulling material from an unseen companion star, heating it to millions of degrees. Some could even be the long-sought seeds of supermassive black holes, the mysterious precursors that somehow grew to dominate the centers of galaxies. Their anonymity is the central problem. Without knowing what kind of object we are looking at, we cannot understand its life cycle, its power, or its role in the cosmic ecosystem. It is like having a list of names with no faces, no histories, and no addresses. Every unidentified source is a closed door, and behind each one could be a completely new chapter in our understanding of the high-energy universe. Solving this requires more than just powerful telescopes. It demands a new way of seeing, a method to give these phantoms a name and a story. These invisible phantoms lead us directly to an even grander cosmic shortfall. For decades, astronomers have faced a troubling inventory problem. When they tally all the normal matter in the universe, the stuff that makes up every star, planet, and person, a staggering amount is simply missing. This is the mystery of the missing baryons. Based on our most precise measurements of the early universe, we know exactly how much of this ordinary matter should exist today. Yet when we count everything we can see, from galaxies to gas clouds, we find only about half of what the calculations demand. An entire half of the universe's normal material has vanished without a trace. So where did it all go? The most compelling theory points to the largest structure in existence, the cosmic web. This is the intricate, spider-like network of filaments made of dark matter, upon which galaxies are strung like glittering beads. Theorists suggest that the missing baryons are not in galaxies at all, but are spread throughout these vast, invisible filaments in the form of an incredibly thin, superheated gas. This gas is so hot, reaching temperatures of millions of degrees, that it does not emit visible light. Instead, it shines faintly in X-rays. This is where the cosmic X-ray background provides a crucial clue. That faint, all-pervasive glow we detect could be the combined whisper of this very gas, the signature of the missing baryons spread across the cosmic web. Proving this is one of the greatest challenges in modern cosmology. The gas is so diffuse that its signal is almost impossibly weak, lost in the sea of other X-ray sources. It is like trying to hear a single person whispering in a roaring stadium. Pinpointing this signal and mapping its distribution would not only solve the mystery of the missing matter, but it would allow us to see the hidden skeleton of the cosmos itself, the brilliant architecture upon which everything is built. Among the countless invisible phantoms lighting up the X-ray fog, one class of object stands out as a true titan of power. These are the active galactic nuclei, or AGN, the fiercely bright hearts of distant galaxies. At the center of each one lies a supermassive black hole, a gravitational monster with a mass millions or even billions of times greater than our Sun. When these colossal entities are actively feeding, pulling vast amounts of gas and dust into their grasp, the material does not simply vanish. It forms a searingly hot, spinning disk of doomed matter, an accretion disk that heats up to millions of degrees. This incredible heat causes the disk to blaze with X-ray light, turning each active nucleus into a lighthouse beam of high-energy radiation that can outshine every star in its home galaxy combined. For a long time, scientists believed these cosmic engines were the primary source of the entire X-ray background, the singular answer to the ghostly glow. The logic was compelling. If you add up the light from every AGN across the universe, could their combined output explain everything we see? The answer, as it so often is in cosmology, is more complex than we hoped. While AGN are undoubtedly major players, they may not be the sole dominant source. The unresolved portion of the background, the part that even our best telescopes cannot break into individual points, suggests other contributors are at work. This unresolved glow is a clue that the universe is hiding other, fainter sources of X-rays. Could it be the collective whisper of millions of distant, normal galaxies, where countless stellar mass black holes and neutron stars are adding their own faint voices to the chorus? Or perhaps it is the signature of that superheated gas in the cosmic web, the very material of the missing baryons. The debate forces us to question our understanding of cosmic budgets. If AGN are not the sole architects of this pervasive light, then what other hidden phenomena are we failing to account for in the high-energy sky? The true composition of the background remains a balancing act, a cosmic puzzle where we are still trying to weigh the contributions of the brilliant lighthouses against the combined glow of countless, unseen campfires. But our census of these brilliant monsters is fundamentally incomplete. For every active galactic nucleus we see blazing openly across the cosmos, there could be another, perhaps even more numerous population hiding in plain sight. These are the obscured active galactic nuclei shrouded behind thick cosmic veils of gas and dust. Imagine a lighthouse surrounded by an impenetrable fog. You know a powerful beam is there, you can sense its energy, but you cannot see the light itself directly. This is the nature of these hidden monsters. Their visible light and even some of their lower energy radiation is blocked by the dense, donut-shaped structure of material swirling around the central black hole. Yet high-energy X-rays are so penetrating they can punch through this obscuring shroud. While the fog absorbs the lighthouse's visible beam, the deep rumble of its powerful engine still shakes the air. To our telescopes, these hidden active nuclei appear as powerful X-ray sources with remarkably faint or entirely missing counterparts in optical light. They are the ghosts within the machine, contributing a massive amount of power to the cosmic X-ray background while remaining almost invisible to our traditional surveys. This creates a huge problem for our cosmic accounting. If we only count the active galactic nuclei we can see directly, we are missing a colossal part of the story. How do we find something designed to not be seen? The techniques astronomers use are acts of cosmic deduction. One method is to look for very specific, telltale signatures in the X-ray light itself. When X-rays bombard the thick clouds of gas, they can cause the atoms in that gas to fluoresce, emitting a very specific, sharp energy signature like a fingerprint. Detecting this fluorescent glow is a sure sign that our view of the central engine is blocked, and we are seeing the reflected light from its hidden surroundings. Another approach is to use infrared telescopes. While the dust blocks visible light, it absorbs that energy and re-radiates it as heat, glowing brightly in the infrared part of the spectrum. So, a powerful X-ray source that is also a bright, hot spot in the infrared is a prime candidate for an obscured active galactic nucleus. Finding these hidden giants is more than just filling in a missing column in a ledger. It forces us to reconsider the life cycle of these cosmic beasts. Is obscuration a phase that every active galactic nucleus goes through, a messy, dusty youth before it blows away its surrounding material and shines openly? Or are there entire populations of black holes that spend their entire lives veiled, their true power only hinted at by the faint, high-energy tremor we detect from across the universe? Uncovering these hidden monsters is key to understanding whether the faint, unresolved portion of the X-ray background is in fact the collective murmur of countless shrouded black holes, their combined voices creating the universe's permanent, ghostly hum. These hidden monsters are not the only giants adding their voice to the cosmic chorus. The universe's largest structures, the immense galaxy clusters, also radiate with a powerful X-ray hum of their own. Each cluster is a metropolis of thousands of galaxies, all bound together by the irresistible grip of gravity. But the galaxies themselves are only the visible tip of a much larger, darker iceberg. The true bulk of a cluster's mass is the mysterious dark matter, whose gravity creates a deep well, and trapped within that well is a vast ocean of superheated gas. This gas is not merely warm, it is searing, with temperatures soaring to over 100 million degrees. At such extreme heat, the gas particles move at ferocious speeds, and when they collide, they release their immense energy as X-ray photons. A single, nearby galaxy cluster can shine so brightly in X-rays that it appears as an extended glowing cloud, a brilliant smudge against the darker background. The question for cosmologists is not whether clusters contribute to the all-sky glow, but exactly how much. Quantifying their total contribution across the entire history of the universe is a monumental challenge. We can see the bright, nearby clusters clearly, but what about the faint, distant ones? In the early universe, clusters were still assembling, and their gas may have been hotter, denser, or more widespread. The light from these infant clusters is incredibly faint, stretched and diluted by the expansion of space over billions of years. This light blends seamlessly into the unresolved portion of the X-ray background, making it nearly impossible to distinguish a distant cluster's faint glow from the combined light of a million hidden black holes or the whisper of the cosmic web. Is the unresolved background dominated by these colossal but distant gas clouds, or is their collective voice just one part of a much larger choir? Solving this requires more than just sharp images. It demands a new way of listening, of separating the deep bass note of a galaxy cluster from the higher-pitched whine of an active black hole. Until we can accurately tally the X-ray output of clusters across all of cosmic time, we cannot know the true balance of power in the high-energy universe, leaving a fundamental piece of the background's origin shrouded in the fog of deep space. The brilliance of active galactic nuclei presents a deceptive picture. For every colossal beacon outshining its galaxy, there could exist 1,000 quiet neighbors, their engines humming at a barely perceptible level. This is the enigma of the faint end, the vast population of low-luminosity active nuclei that may form the true bedrock of the X-ray background. These are not the titans blazing across the cosmos, but the dim embers, the supermassive black holes that are feeding slowly or intermittently. A single one of these quiet giants emits only a faint trickle of X-rays, a whisper compared to the roar of its active cousins, yet their numbers could be staggering. If nearly every galaxy, including quiet ones like our own Milky Way, hosts a supermassive black hole that occasionally snacks on a passing gas cloud or star, then the cumulative glow from these countless faint events could be immense. The unresolved portion of the X-ray background might not be a true fog at all, but the combined light of every quiet black hole in the universe, a sea of dim candles whose collective radiance creates a permanent, uniform shine. So why can't we see them? The challenge is one of cosmic distance and technological limits. Our most powerful X-ray telescopes, like Chandra, are incredible instruments, but they have a fundamental threshold. They can only detect an individual source if its signal is significantly stronger than the inherent background noise of the detector itself and the universe. A faint, low-luminosity active nucleus in a distant galaxy falls below this threshold. Its whisper is simply too quiet to be heard over the constant hum of space. It is like trying to spot a single, specific firefly's glow from an airplane flying high above a massive, darkened city. You see the combined glow of millions of lights, but no single pinprick stands out. This is our fundamental limitation. We know the faint sources must be there. Our theories of galaxy evolution demand it, but our current tools cannot resolve them individually. This missing population creates a critical gap in our understanding. Are these quiet black holes the true dominant contributors to the background, their collective power dwarfing that of the brilliant but rare active galactic nuclei? Or is their role more modest? Until we can peer deeper and detect these faint embers directly, a fundamental piece of the cosmic X-ray puzzle will remain hidden in the shadows, forcing us to wonder if the universe's greatest light show is actually powered by its quietest inhabitants. The very shape of this ghostly light holds its own profound secret. When scientists spread the cosmic X-ray background out into its constituent energies, like separating white light into a rainbow, they found a pattern that defies simple explanation. This energy distribution, called the spectrum, has a specific, recognizable curve. For decades, the leading theory held that this shape was simply the sum of all the active galactic nuclei out there. If you added up the spectra of every single one, from the brightest quasars to the faintest hidden monsters, their combined light should perfectly match the spectrum of the background. But it does not. The puzzle lies in the highest energy X-rays. The combined light of all known active galactic nuclei seems to fall short at these extreme energies, leaving in excess an unexplained bump in the high-energy part of the cosmic spectrum. It is as if you were listening to a symphony and could identify every instrument from the violins to the cellos, but you keep hearing a deep, resonant note that no instrument in the orchestra is playing. Something else is adding its voice to the cosmic chorus, something we have not yet identified. This spectral mismatch points to one of two thrilling possibilities. The first is that a completely unknown population of X-ray sources exists, objects that naturally produce more high-energy radiation than the active black holes we are familiar with. What could these be? Perhaps a new class of hyper-energetic stellar explosions, or exotic types of neutron stars with magnetic fields of unimaginable strength. The second, even more radical possibility is that our understanding of the physics itself is incomplete. The processes that generate X-rays around black holes or in hot gas might operate in ways we have not yet theorized, under conditions so extreme that they reveal new laws of high-energy emission. This is not just a missing ingredient, it is a fundamental clue that the universe is still hiding either new types of objects or new rules of behavior, their signature written plainly in the energetic curve of the oldest light we can see. This unresolved spectral mismatch forces us to look back in time. The ghostly light we see today is a cosmic fossil, a layered record of events that unfolded over billions of years. To understand its true composition, we must trace the life stories of its contributors, asking not just what they are, but how they lived and died across the history of the universe. This is the grand mystery of cosmic evolution. The X-ray background is not a static picture. It is a movie playing on a screen 13 billion light-years wide, and we are seeing only the final, single frame. The brilliance of active galactic nuclei was not constant. In the early universe, they were far more active and numerous, a frenzied era of black hole feasting and growth. The most distant, ancient quasars are some of the most luminous objects ever seen, their light blazing across space as their central black holes gorged on the abundant gas of the young cosmos. This means their contribution to the X-ray background was vastly different in the past. The faint glow we detect from a particular patch of sky today is not the combined light of sources all shining at once. It is a palimpsest, a layered document where the brilliant, short-lived flash of a quasar from 10 billion years ago is superimposed onto the fainter, more constant murmur of a nearby galaxy cluster. Separating these layers is like trying to reconstruct the entire history of a city by listening to the blended noise of its traffic, conversations, and construction from a single moment in time. You can hear the hum, but distinguishing the roar of a long-demolished factory from the quiet chatter of a modern cafe is nearly impossible. This is the core challenge. We know the populations of X-ray sources evolved dramatically, but we do not have a clear timeline of their rise and fall. Did the number of active black holes peak at a specific cosmic epoch and then slowly decline as the universe expanded and fuel became scarcer? Or were there multiple waves of activity driven by galactic collisions that funneled fresh material into dormant black holes? The answers are written in the faint, unresolved light, but our eyes are not yet sharp enough to read them. Understanding this evolution is not just an academic exercise. It is the key to unlocking the life cycle of the universe's most powerful engines and to finally reading the story hidden within the oldest light in the sky. While the titans of the cosmos command our attention, a much more local drama may be contributing its own unique whisper to the background hum. Look inside any bustling star-forming galaxy, a place where new suns are born in vast, glowing clouds of gas and dust. This process of creation is not a gentle one, it is a violent, chaotic affair. Among the newborn stars, massive ones live fast and die young, exploding as supernova and leaving behind dense stellar corpses, neutron stars, and black holes. Many of these remnants do not linger in isolation. They often form binary systems locked in a gravitational dance with a living companion star. As they orbit, the intense gravity of the dead star can rip material from its partner, funneling it into a searingly hot disk of accreting matter. This process heats the gas to millions of degrees, causing it to blaze with X-rays. These systems are called X-ray binaries, and they are the hidden power plants of star-forming galaxies. In a galaxy like our own Milky Way, we can observe individual X-ray binaries flickering and flaring. but in a distant, star-bursting galaxy, the combined output of thousands or even millions of these systems would blend into a single, unresolved fog of X-ray light. This collective glow from all the star-forming galaxies across the universe could be a significant and previously overlooked piece of the cosmic X-ray background puzzle. The debate among astronomers is fierce. How significant is this link truly? Some argue that the combined might of all these stellar engines is the missing component, especially at certain energies, finally explaining the spectral mismatch that the black hole models could not. Others contend that while star formation contributes, it is a secondary player, a faint chorus compared to the roaring solo of the active galactic nuclei. The challenge lies in the immense distances. We can study individual X-ray binaries in our galactic neighborhood, but in a faraway galaxy, we cannot resolve them individually. We only see their combined, blended light. Determining the exact X-ray output from star formation alone is like trying to measure how much every single car engine in a distant city contributes to its overall noise level from miles away. You know the sound is there, but separating it from the hum of factories and power plants is incredibly difficult. This debate forces us to reconsider the very nature of cosmic energy. Is the high-energy sky dominated by the few colossal monsters at the centers of galaxies, or is it built from the combined, steady work of countless smaller, stellar-scale engines, each one a testament to the violent life and death of stars? The answer could redefine our understanding of how the universe's most common forms of creation add their voice to its oldest song. The brilliant light of a distant quasar acts as a cosmic flashlight, illuminating the dark expanses between the galaxies. As this powerful beam of X-rays travels for billions of years on its journey to our telescopes, it does not pass through empty space. It pierces through a diffuse, invisible medium, a vast collection of warm gas clouds floating in the void. When the light finally reaches us, scientists can spread it out into a spectrum, a unique energy signature, and they find something astonishing. Etched into that spectrum are countless fine, dark lines. This is the X-ray forest, a dense thicket of absorption lines where the light at very specific, precise energies has been subtly stolen. Each dark line is an imprint, the fingerprint of a particular chemical element like oxygen or neon within an invisible cloud of intergalactic gas. The location of the line tells us which element we are seeing, and the precise shade of the line reveals the cloud's physical state, its temperature, density, and even its motion. This is how we can begin to trace the ghostly architecture of the cosmic web. Each absorption line is a data point, a single stitch in the invisible tapestry. By analyzing the forest of lines from a single quasar, astronomers can map the distribution of gas clouds along that one narrow line of sight. It is like seeing the silhouette of a forest against a distant spotlight, revealing the presence of individual trees. The grand challenge, the true mystery, is moving from that single line of sight to a full, three-dimensional map. We need to point our cosmic flashlights in thousands of different directions at quasars scattered across the sky to piece together the structure from countless individual threads. But the gas in these filaments is incredibly diffuse, so thin that its absorption signal is whisper-quiet and easily lost in the noise. The very existence of the X-ray forest confirms that a vast reservoir of warm, intergalactic gas is out there, the prime candidate for the universe's missing baryons. Yet, measuring its exact properties, its true total mass, and its detailed distribution remains one of observational cosmology's most delicate tasks. Are we seeing the main arteries of the cosmic web, or just the faint, wispy outskirts? The answer lies in deciphering the subtle code written in the dark lines of this ancient high-energy light. The uniform glow of the X-ray background is a cosmic lie. Look closer with instruments of exquisite sensitivity, and you will find that the fog is not perfectly smooth. It is mottled with incredibly subtle variations, tiny bright and dark patches that form a complex pattern across the entire sky. These are the anisotropies, the fluctuations in the background, and they hold a secret map of the universe's largest structures. Think of it like listening to the constant roar of a distant ocean. At first, it sounds like a uniform noise, but if you listen carefully, you can detect the rhythm of individual waves crashing, groups of waves arriving together. These patterns tell you something about the coastline and the storms far out at sea. In the same way, the fluctuations in the X-ray background are not random. They are a direct imprint of how the sources of this light are clustered together across billions of light years. If active galactic nuclei tend to live in the dense knots of the cosmic web, their light will create a specific pattern of bright spots in the background. If the faint, unresolved galaxies are spread more evenly along the web's filaments, they will produce a different, subtler pattern of variation. Interpreting this cosmic fingerprint is one of the most complex challenges in modern astrophysics. The problem is that we are hearing a chorus of countless different voices all at once. The fluctuation pattern we measure is not from one type of source, but a messy overlap of every contributor. The sharp, clustered signal from a group of nearby active black holes is superimposed on the fainter, broader fluctuation from distant galaxy clusters, which is itself blended with the ultra-faint whisper from the hot gas in the cosmic web. Disentangling this single, observed pattern into its individual components is like trying to identify every instrument in an orchestra by listening to a single, combined chord recorded from outside the concert hall. Each type of source has its own unique clustering signature, its own preferred scale. By studying how the strength of the fluctuations changes across different angular sizes on the sky, from fine specks to broad patches, cosmologists can perform a statistical autopsy on the background. They can ask, does the data match a universe where the primary sources are highly clustered black holes, or one where it is dominated by more evenly distributed star-forming galaxies? The answer is written in the light, a faint, scrambled code that, if cracked, would not only tell us what powers the cosmic X-ray glow, but would allow us to trace the invisible architecture of the entire universe, seeing the gravitational blueprint of dark matter itself through the eyes of its most energetic light. But the deepest secret of this ancient light is written at its most extreme energies. Beyond the familiar glow lies a very high energy component, a faint yet persistent signal of X-rays so powerful they defy easy explanation. These are not the typical photons from a hot gas or a feeding black hole. They are the universe's most energetic bullets, and their origin is one of the most hotly debated topics in high-energy astrophysics. One of the primary suspects is a special class of active galactic nuclei known as blazars. Imagine a black hole engine pointed almost directly at Earth, its relativistic jet of particles and radiation firing a cosmic blowtorch straight down our line of sight. This alignment makes blazars appear incredibly bright and violently variable, capable of producing the kinds of extreme energies we detect. But when astronomers tally the total number of known blazars, their combined output still seems to fall short of accounting for the entire very high energy background. There is a residual glow that remains unclaimed, pointing to the existence of other, even more exotic sources. This opens the door to a truly radical possibility that we are seeing the indirect signature of dark matter. Some leading theories suggest that dark matter could be made of hypothetical particles, such as sterile neutrinos or weakly interacting massive particles. If these particles are unstable, they could slowly decay over billions of years, and that decay process would release a very specific, faint signature of high-energy X-rays. Detecting this signal would be a monumental breakthrough, our first direct glimpse into the nature of the universe's dominant yet invisible substance. The challenge is that this predicted signal is incredibly weak, easily confused with the combined murmur of countless distant astrophysical sources. Is that stubborn, unresolved excess at the highest energies the whisper of dying dark matter? or is it simply a vast population of faint, undiscovered blazars whose individual lights are too dim for our telescopes to resolve? Or could it be something entirely new, a type of cosmic event or object so extreme that we have not yet even conceived of its existence? The answer lies at the very edge of our perception, a faint tremor in the most energetic light that could either reveal the particles that shape the cosmos or force us to rewrite the book on the universe's most violent phenomena. Deep in the heart of galaxies, a silent predator lies in wait. A supermassive black hole, dormant and dark, exerts an immense gravitational pull on the stars orbiting it. When a star wanders too close, it is subjected to forces beyond comprehension. The black hole's gravity, vastly stronger on the side of the star nearest to it, stretches the star horribly, pulling it into a long, thin stream of gas in a cataclysmic event known as a tidal disruption. This stream of stellar material then wraps around the black hole, colliding with itself in a chaotic whirlpool of destruction. The resulting friction heats the gas to temperatures of millions of degrees, triggering a brilliant, short-lived flare of X-ray light that can outshine the entire galaxy for a few brief months. This is a tidal disruption event, one of the most violent and transient spectacles in the cosmos. Each one is a singular cosmic disaster, a star being shredded into a glowing banquet for a hidden monster. But could these brief, brilliant flashes scattered across space and time add up to something more? When we look at the faint, permanent glow of the X-ray background, we are seeing the accumulated light of the entire universe. Is it possible that the combined history of all these stellar cataclysms contributes a meaningful fraction of that ancient radiance? The challenge lies in their fleeting nature. A tidal disruption event is a spectacular flash in the pan, a brilliant blaze that quickly fades into darkness. To contribute to the steady, uniform background, these events would need to be happening constantly, somewhere in the universe, with such regularity that their fading light overlaps, creating a permanent, flickering glow. It is like trying to create a constant, even light using only camera flashes in a vast, dark stadium. If enough people take a flash photograph at random moments, the combined effect from a distance could appear as a faint, continuous shimmer. The question for astronomers is one of cosmic statistics. How often do these events actually occur? Is every galaxy host to a tidal disruption every 10,000 years or every million? The rate is critical. If they are too rare, their total contribution to the background would be negligible, a few bright sparks lost in a sea of light. But if they are more common than we think, especially around certain types of black holes, their collective history could be written into the unresolved portion of the X-ray fog. This forces us to listen to the background not as a single hum, but as a chorus of countless whispers where the final, fading cry of a devoured star from 1 billion years ago might still be adding its tiny, almost imperceptible voice to the universe's oldest song. This diffuse, superheated gas is known as the warm-hot intergalactic medium, or WIM for short. It is the universe's ultimate ghost, a form of matter so ethereal that proving its existence has pushed our technology to the absolute limit. Theorists are confident the WIM is out there, a sprawling ocean of gas heated to hundreds of thousands, even millions of degrees, woven through the dark matter filaments of the cosmic web. This is not a gentle warmth, it is the searing heat imparted by the universe's own violent growth, as matter collapsed into the web under the relentless pull of gravity. Finding this gas is the definitive key to closing the case of the missing baryons, but how do you capture a ghost that is barely there? The gas is so incredibly thin, with densities a mere 10 to 100 times the average density of the entire universe, that its signal is almost vanishingly weak. It is like trying to detect a single, warm breath dispersed throughout an entire, empty cathedral. The primary method for hunting the WIM relies on those same cosmic flashlights, the distant quasars. As their powerful X-ray beams pass through these filaments, the superheated gas should imprint a specific signature, a subtle smearing or a set of faint absorption lines from highly ionized oxygen and neon onto the quasar's spectrum. But these lines are not the sharp, dark features of the X-ray forest. They are broad, shallow, and incredibly difficult to distinguish from the background noise. It is the difference between seeing the clear silhouette of a tree and trying to make out the faint, shimmering heat haze rising from a distant road. Confirming even a single detection is a triumph, requiring immense observational time and the most sensitive instruments we have. Each tentative detection is a data point, a single thread of evidence for this vast, hidden reservoir. The ultimate goal is to move beyond these few, precious lines of sight and create a three-dimensional map of the WIM to trace the glowing, tenuous veins of the cosmic web itself. Success would do more than just find the missing atoms. It would validate our entire model of cosmic structure formation. It would show us how the primordial soup of the Big Bang was cooked and distilled into the galaxies we see today, confirming that the grand architecture we predicted is not just a theoretical dream, but a physical reality, its final, hidden component finally brought into the light. 13 billion years ago, the universe was a featureless sea of darkness. This was the cosmic dark ages, a time after the primordial fireball of the Big Bang had faded, but before the first stars had ignited. The transformation that ended this epoch is one of the most profound in cosmic history, a period called reionization. For the first few 100 million years, the universe was filled with a thick, neutral hydrogen fog, absorbing the faint, early starlight and keeping the cosmos opaque. Then something happened to clear the fog. The first generations of brilliant, massive stars are often credited with this task, their intense ultraviolet radiation blasting apart the hydrogen atoms, stripping away their electrons and ionizing the gas, turning the universe transparent. But there is a compelling mystery here. Could the cosmic X-ray background hold a forgotten chapter of this story? The hypothesis is that the very first X-ray sources, the earliest black holes and X-ray binaries, played a silent, supporting role in this cosmic dawn. While the first stars provided the raw ultraviolet power, their light was easily absorbed by the dense pockets of hydrogen around them, creating localized bubbles of ionized gas. X-rays, however, are far more penetrating. They could travel vast distances through the neutral fog, depositing their energy evenly and gently heating the entire intergalactic medium. This widespread heating would have made it easier for the ultraviolet light from stars to finish the job of ionization, like warming a vast block of ice so that sunlight can melt it more efficiently. This subtle X-ray heating may have been the crucial catalyst that allowed the universe to become fully transparent. The problem is that observing this ancient signal is one of the most difficult challenges in all of astronomy. The X-ray light from these first, feeble sources is incredibly faint, and its journey to us has stretched over more than 13 billion years. The expansion of the universe has redshifted this radiation, stretching its high-energy X-rays down into the softer, lower-energy part of the spectrum, where they are lost in a sea of local galactic foregrounds. It is like trying to hear the first, faint notes of a symphony from the other side of the world, with the entire sound distorted and buried under the noise of a modern city. Our current X-ray telescopes simply do not have the sensitivity to peer that far back and isolate this primordial whisper. The next generation of observatories, however, are being designed with this very goal in mind. They will be listening for the faintest echo of that long-vanished heat, the signature of the first black holes stirring in the darkness, whose gentle warmth may have been the unsung hero that helped light up the cosmos. The ancient light holds its secrets tight, even after we account for every known quasar, every hidden monster, and every distant galaxy cluster. A stubborn fraction of the X-ray background refuses to be explained. This is the unresolved portion at high redshift, a ghost within the ghost, and it points to a profound gap in our knowledge of the infant universe. Redshift is our measure of cosmic distance, the stretching of light's wavelength as space itself expands. A high redshift means we are looking back to a time when the universe was young, hot, and fundamentally different from the cosmos we see today. It is in this primordial era that our census of X-ray sources becomes most incomplete. Our telescopes, for all their power, simply cannot see the faintest objects from that distant epoch. Their light is too diluted, their whispers too quiet. So what exotic inhabitants of the early universe are we missing? The possibilities are as thrilling as they are mysterious. One compelling idea is a population of the very first black holes, forming from the direct collapse of immense gas clouds in the darkness before the first stars finished lighting up the cosmos. These primordial black holes would have been unique beasts, feeding in a universe rich with unused fuel, potentially generating X-rays in ways we have not yet observed. Another candidate is a vast number of highly obscured active nuclei, so shrouded in the thick dust and gas of the young galaxies that even their high-energy radiation is heavily muffled, leaving only the faintest trace in our detectors. Or perhaps the early universe hosted a completely different kind of stellar death, with the first generations of stars exploding in hypernova so violent they unleashed torrents of X-rays unlike anything produced by modern supernova. Each of these possibilities challenges our understanding of cosmic evolution. If the unresolved background is dominated by these ancient, unseen sources, it means the early universe was far more energetically active in X-rays than our current models predict. It suggests a frantic, hidden chapter of black hole growth and stellar cataclysm that set the stage for everything that followed. The lingering glow is a fossil of that forgotten dawn, a direct message from an era we are only just beginning to probe. Unlocking this mystery will require more than just bigger telescopes. It demands a new vision of the cosmos in its infancy, a realm where the rules themselves might have been written in a different, more violent tongue. Our own galactic backyard adds its own complicating whisper to the cosmic signal. The Milky Way is surrounded by an immense spherical halo of superheated gas, a vast atmosphere reaching far beyond the familiar spiral of its starry disk. This gas, heated to millions of degrees by supernova explosions and perhaps even by outbursts from our own central black hole, glows faintly in X-rays. It is a local fog, a brilliant veil hanging right in front of our cosmic window, for astronomers trying to peer through it to see the true, ancient background. This halo presents a monumental challenge. How do you distinguish the faint, uniform light from billions of light years away from the shimmering glow of your own home's atmosphere? The process is one of meticulous subtraction. Scientists must create a detailed model of our galaxy's X-ray emission, mapping its intensity and temperature in every direction. They then attempt to subtract this local foreground from the total signal they receive. What remains, in theory, should be the pristine cosmic X-ray background, but the model is never perfect. The halo's structure is complex and patchy, its exact temperature and density difficult to measure with absolute certainty. Any error in this subtraction pollutes the cosmic signal, leaving behind artifacts that could be mistaken for features of the distant universe. This local interference forces a humbling realization. To understand the cosmos at its largest scales, we must first achieve a deep and intimate knowledge of our own celestial neighborhood. The properties of our galactic halo are not just a nuisance, they are a history book. The temperature and extent of this hot gas tell a story of the Milky Way's violent past, of countless stellar explosions that have enriched and energized its surroundings over billions of years. By studying this local fog in exquisite detail, we not only clean our window to the distant universe, we also read the autobiography of our own galaxy, written in the faint, hot breath that surrounds it. The ghostly X-ray glow could be a message from the universe's greatest secret. This brings us to the electrifying possibility that the cosmic X-ray background is not just from black holes or hot gas, but from dark matter itself. Think of dark matter as the invisible skeleton of the cosmos, a substance that exerts gravity but does not emit or absorb light. making it completely undetectable to our telescopes. Yet, what if this mysterious substance is not entirely silent? Some of the leading theories suggest that dark matter could be made of exotic particles, such as sterile neutrinos or weakly interacting massive particles. If these particles are unstable, they could very slowly decay over billions of years. Alternatively, if they occasionally collide and annihilate one another, these processes would release energy. That energy would manifest as a very faint, specific signal of X-ray photons. This would not be a brilliant flash, but a subtle, uniform whisper woven into the fabric of the entire sky, a permanent testament to the slow transformation of the universe's dark foundation. The challenge, of course, is finding this whisper. The predicted signal is incredibly weak, a specific energy signature that must be distinguished from the roaring chorus of all the other X-ray sources, from active galactic nuclei to distant galaxy clusters. It is like trying to hear a single, specific note from a single instrument that is always playing, while standing in the middle of a roaring heavy metal concert. Astronomers are hunting for this signature by staring at places where the dark matter is thought to be most concentrated, such as the centers of nearby galaxies or the diffuse halos of galaxy clusters. They take incredibly detailed spectra of the X-ray background in these regions, searching for a tiny, unexplained bump at a very precise energy, a spike that cannot be attributed to any known atom or astrophysical process. Finding it would be one of the most profound discoveries in the history of science, a direct window into the nature of the substance that shapes the cosmos. Yet the search continues, a meticulous process of elimination that pushes our instruments to their absolute limits, all to answer a single, haunting question. Is the oldest light in the universe quietly telling us what the dark side is made of? Even the solar wind may be adding its own faint voice to the cosmic chorus. A process called charge exchange offers a surprisingly local and elegant way to create X-rays, right here in our own cosmic neighborhood. The mechanism is beautiful in its simplicity. Our sun constantly blows out a stream of charged particles, the solar wind, mostly protons and electrons. When this wind encounters a cloud of neutral gas, like the hydrogen that drifts through the interstellar medium or the vast envelope of a comet, something fascinating happens. A charged ion from the solar wind, hungry for an electron, can steal one from a neutral atom in the gas cloud. This exchange leaves the ion in an excited, unstable state. To regain its balance, it almost immediately releases this excess energy, emitting an X-ray photon in the process. It is a tiny, atomic handshake that produces a spark of high-energy light. This phenomenon is not just theoretical, we have observed it directly. When a comet swings through our solar system, its large, gaseous coma provides a perfect target for the solar wind. Satellites have detected a distinct, soft X-ray glow emanating from these comets, a clear signature of charge exchange at work. The question for cosmologists is one of scale. Could this process be happening so ubiquitously throughout our galaxy and others that its collective glow becomes a significant part of the faint, uniform X-ray background we see? The debate hinges on the distribution of neutral gas. Is the space between stars filled with enough diffuse hydrogen to make the entire Milky Way's halo shimmer with the X-rays from countless charge exchange events? If so, then a portion of what we thought was a cosmic signal might actually be a local fog, a permanent, soft X-ray aurora generated by our galaxy's own weather. Untangling this contribution is critical for achieving a clean view of the distant universe. If we misattribute this local whisper to the ancient background, we risk misunderstanding the true energy output of the early cosmos. This subtle atomic process reminds us that the universe is full of surprises, and sometimes the key to the grandest mystery lies in understanding the smallest of interactions. Our technological eyes on the X-ray sky are themselves a source of profound mystery. Instruments like Chandra, XMM Newton, and Swift are engineering marvels, yet they are fundamentally constrained by two simple physical limits. The first is collecting area, a measure of how much light a telescope can gather. Imagine trying to catch rain in a thimble. No matter how long you stand in a downpour, you will only collect a tiny amount of water. Our current X-ray telescopes are like that thimble. Their mirrors are relatively small, so they can only capture a faint trickle of the universe's high-energy photons, especially from the most distant and faintest sources. The second limit is angular resolution, the ability to distinguish two separate points of light. Chandra has phenomenal vision, akin to being able to read a newspaper from half a mile away. But even its sharp eyes cannot separate the faintest, most crowded specks of light in the deepest fields. They blend together into an unresolved haze, the very fog we are trying to decipher. This instrumental blurring means we cannot be sure if the unresolved background is a true, smooth fog of gas or just a sea of sources too close together for any telescope to untangle. Beyond these physical constraints, our tools also have a kind of energy blindness. Each instrument has a specific energy range where it performs best, a limited window into the full X-ray spectrum. A source that shines brightly at one energy might be completely invisible at another, leading to a biased census of the cosmos. The very act of observing creates gaps in our knowledge, blind spots dictated not by the universe but by the design of our own machines. We are, in a very real sense, trying to map a continent by peering through a keyhole, knowing that the view is fragmented and incomplete. Our current keyhole view of the cosmos is about to be blown wide open. The next generation of X-ray observatories, like the European Space Agency's Athena and the proposed Lynx mission, are not merely incremental improvements, they are revolutionary leaps designed to see the unseen. Imagine trading a thimble for a vast rain barrel and a keyhole for a floor-to-ceiling window. Athena, the advanced telescope for high-energy astrophysics, will have a collecting area more than 100 times larger than any current X-ray telescope. This colossal light-gathering power means it will not just see the brightest beacons, it will detect the faintest whispers, the individual embers of low-luminosity black holes and distant star-forming galaxies that currently blur into the unresolved background. It will be sensitive enough to take the spectrum of this faint light, reading its energy signature with exquisite precision to finally identify what these countless dim sources truly are. Meanwhile, the Lynx Observatory is designed to have vision so sharp it could resolve a single star at the distance of the Andromeda Galaxy, but in X-ray light. Its phenomenal angular resolution will act like a cosmic scalpel, slicing through the X-ray fog to separate every single point source in a deep field, leaving behind only the true, diffuse components like the hot gas of the cosmic web or the possible signal from dark matter. Together, these observatories will do more than just add to our list of known objects. They will transform the background from a uniform hum into a detailed symphony where we can finally hear each individual instrument. They will map the warm-hot intergalactic medium in 3 dimensions, tracing the glowing veins of the cosmic web and definitively weighing the universe's missing baryons. They will stare into the hearts of newborn galaxies in the early universe, witnessing the formation of the first supermassive black holes and understanding their role in cosmic dawn. The very mysteries that have persisted for decades, from the spectral mismatch to the nature of the unresolved glow, are the specific puzzles these telescopes were built to solve. The faint, ancient light has been holding its secrets for billions of years, but its time of revelation is fast approaching. The faint X-ray glow begins to speak when we listen to it in harmony with the rest of the cosmos. This is the power of cross-correlation, a statistical technique that acts like a cosmic tuning fork, allowing us to hear the hidden relationships between different forms of light. The method itself is a work of elegant deduction. Astronomers take a deep, unresolved map of the X-ray background, a seemingly random collection of bright and dim pixels, and they place it over a similar map of the same patch of sky, but in a completely different wavelength like the infrared or radio. They then ask a simple question: do the faint, blurry X-ray bright spots tend to line up with the faint, blurry infrared bright spots? If they do, it means the invisible sources powering the X-ray glow are physically connected to the objects creating the infrared light. It is like trying to identify a masked singer by matching the rhythm of their voice to the unique tap of their foot. You cannot see the singer, but the synchronized patterns give their identity away. This technique has already yielded profound insights. A strong correlation has been found between the unresolved X-ray background and deep infrared maps from telescopes like Spitzer and Herschel. The infrared light often comes from vast, dusty galaxies undergoing intense bursts of star formation. The dust absorbs the visible light from all the new stars and re-radiates it as heat in the infrared. The correlation tells us that a significant portion of the mysterious X-ray fog is inextricably linked to these stellar nurseries. But what is the precise nature of that link? Is the X-ray emission coming from the combined power of millions of X-ray binaries within those star-forming galaxies, the natural end product of a bustling stellar population? Or is it revealing something else entirely, like hidden, growing supermassive black holes buried so deep in cosmic dust that their presence is only betrayed by the penetrating X-rays that escape? The correlation confirms a relationship, but it is now up to sharper telescopes and more detailed observations to play matchmaker, to finally introduce us to the individual objects responsible for this cosmic duet. This method probes the fundamental connections that drive galaxy evolution, asking whether the birth of stars and the growth of black holes are locked in a symbiotic dance, each fueling the other across the vast expanse of cosmic time. A giant cold cloud of gas can act as a perfect cosmic screen. This is the ingenious principle behind shadowing experiments, a clever method astronomers use to dissect the X-ray background. Across our galaxy, vast molecular clouds drift through space, immense collections of cold, dense gas and dust so thick they are completely opaque to the X-rays coming from behind them. When we point our telescopes at such a cloud, it casts a distinct shadow against the brilliant backdrop of the cosmic X-ray glow. By carefully measuring the precise dip in intensity within this shadow and comparing it to the brighter emission from the surrounding sky, scientists can perform a kind of cosmic subtraction. The light that vanishes is the distant extragalactic background, the accumulated light from billions of sources far beyond our galaxy. The light that remains, shining from the cloud itself or from the foreground, is our own Milky Way's contribution. It is like holding your hand up to a bright, foggy sky. The silhouette of your fingers reveals the difference between the local haze in the air and the distant light of the sun. These shadowing experiments provide a crucial, independent measurement, a way to calibrate our models and separate the local fog from the ancient cosmic light. But the story does not end with a simple silhouette. By studying the very edges of the shadow where the distant light is just beginning to be blocked, astronomers can also probe the cloud itself. The way the X-ray light scatters and fluoresces at the cloud's boundary reveals the chemical composition and physical state of the cold gas, offering a unique glimpse into the structure of these galactic building blocks. Each shadow becomes a double-sided tool, blocking one source of light to illuminate the nature of another. This technique cuts through the ambiguity, providing hard data on exactly how much of the pervasive glow is a local phenomenon and how much is the true echo of the distant universe. It is a stark reminder that to see the cosmos clearly, we must first learn to read the shadows it casts. These 25 mysteries all circle back to a single, humbling truth. The universe we see is only a tiny sliver of what is actually there. The cosmic X-ray background is a permanent reminder that most of the cosmic drama, the true action of the universe, plays out in a realm completely invisible to our biological senses. We are like people watching a shadow play on a cave wall, trying to reconstruct the full, vibrant world outside from a few faint, dancing silhouettes. Every mystery we have explored, from the hidden black holes to the ghostly web of dark matter, underscores a profound limitation of our perspective. We built our understanding of the cosmos on the light our eyes can see, only to discover that this visible universe is merely the quiet, well-lit suburb of a vast, chaotic, and brilliantly energetic metropolis. This realization is not a failure of science, but its ultimate purpose. The drive to understand this invisible hum, to decode the whispers from the dark, is one of the most fundamentally human endeavors we can undertake. It is the same curiosity that sent our ancestors staring at the stars, wondering what fires burned in that endless night. Now we know the fires are there, blazing in a light we cannot see, powered by forces we are only beginning to grasp. The enduring puzzle of this ancient glow teaches us that the universe is far stranger, more complex, and more wonderful than we ever dreamed. And the search for its final secrets, the relentless pursuit of answers to questions we have only just learned to ask, confirms our deepest need to not just live in the cosmos, but to truly know it. The faint whisper of X-rays we detect from across the cosmos is far more than a simple glow. It is a rich tapestry woven from 25 profound mysteries. Each thread in this tapestry represents a fundamental question about our universe, from the hidden monsters feasting in galactic cores to the ghostly, superheated gas strung along the cosmic web. These puzzles stretch from the dark matter halo enveloping our own Milky Way to the very edge of the observable universe and the first moments of cosmic dawn. Unraveling even a single one of these threads would revolutionize our understanding of reality. The ultimate goal, the prize for solving this grand puzzle, is a unified theory of the high-energy universe. It would show us how supermassive black holes grow from tiny seeds to become titans, how galaxies are built upon a scaffold of dark matter and hot gas, and perhaps even reveal the true nature of the invisible substance that dictates the fate of everything. The next generation of space observatories are already being built for this purpose, designed to listen to the faintest whispers with unprecedented clarity. Their discoveries will not just fill textbooks, they will rewrite them, transforming the ghostly hum we hear today into a brilliant symphony of cosmic revelation. The greatest chapters in our story of the universe have yet to be written, and they are waiting in that ancient, pervasive light.